So Maxwell's equations, we had 4 of them, right?
Yeah.
Let's see what we have so far. And, we had E dot dA is equal to what?
Q enclosed over epsilon naught.
Over epsilon naught. Good. Then we had B dot dA was equal to what?
Mu naught.
Good.
Oh wait.
This one is this is Gauss's law.
Oh yeah.
Okay. Good. So let's review. Yeah. So Gauss's law. Let me write it here. Gauss's law for electricity and for magnetism, right? Notice these surfaces are closed, so not an open surface. Okay. So let me ask you 2 questions on these. Just a quick review so we remember what they mean. The first, the first question is this. Question 1. Here is a plus 7q. I have a minus 3q. And here is a surface, a closed surface. Okay, here's a closed surface. Okay. Can you tell me what E dot dA is? For what? Yeah, so it's going to be the total charge inside the surface over epsilon naught. So good. So it's going to be 4q, right, over epsilon naught, right? It's q enclosed over epsilon naught. Now, right? So that's Gauss's law. We have applied it for this problem. Okay, sounds good. I'm going to give you now the second question. Okay. Any questions on this one? Question 2. Question 2. Ready? I am not. I will attempt to draw it, but I will. It's a pyramid. It's going to be like this. A square area, though, not a rectangle. I know this is a rectangle. In fact, let's make it a rectangular area. So here is a pyramid, and I would have would look like this. So the base is supposed to be parallel to the ground. Okay? So this is the base. So here is the base. How do we do that? Yeah, like this. Let's say this is the length, this is the width, right? And like this. All right. So the bottom is here. This is the bottom. I hope I'm picturing the picture you draw in your mind is, and then the sides are here, right? These are the sides.
Mm-hmm.
Okay? Suppose we have electric field entering from the bottom. Electric field entering from the bottom. Okay. Electric field coming in from the bottom, and that electric field is E. Let's say that's E. Okay. All right. Clear?
Yep.
How much charge is inside the pyramid? 0. Okay. So let me ask you the following. What's Q total? The flux, the total flux. The total flux is 0. Good. Because E dot dA is Q enclosed over epsilon naught, so that's 0. Good. There is no charge enclosed. Okay, excellent. Another way to think about it is electric field lines enter and then they leave. Whatever enters leaves. There is no net entering or net leaving. Okay. How about the flux from the bottom phase? Bottom. So the bottom there, what's the flux to it? Okay. So electric field times area. Okay. So do you agree that it is the electric field times the area, and the area is length times width, right? Okay. This is the area. You're missing one thing. Electric field is coming in. Okay. What's the sign?
Negative.
Which should be negative. Because for a closed surface, the area always points what?
Outward.
Perpendicular and away. Yeah, so it's away. So the area is pointing down. closed area is pointing down, so it will be a minus. Yeah, so this is the area, so the area vector points down. The electric field vector is pointing up, so they're making 108. So the flux is making. All right. What's the flux through the, for lack of a better word, the sides, let's say. Sides. All the sides, this triangle, this triangle, this triangle, this triangle. What's the total flux through them?
ELW.
Good, yes. Good. So EL comes down. It's just the opposite, yeah. Because we know the total, if you add the bottom plus the sides, that's a closed surface, and the flux through this closed surface is zero. There is no charge inside it. Good. So if you find your, if you get, I don't think I had it in the homework. So if you find yourself doing a complicated problem where you need the height and the angles and you're doing all kinds of dot products and cosines, probably it's wrong because you're working too hard. Okay, so anyways, that was my quick review of Gauss's law. Yes?
Sorry, if you're finding the flux right on the surface, isn't Q equals over epsilon naught? Like it can't do that anymore. So what formula are we using for that?
Flux, the definition of flux is electric field times area. E dot A. Yeah. The flux by definition is E dot EA.
If there was boundary difference in
Or
dot,
instead of dot.
yeah, because you continue with lines on.
Yeah. I'm not sure what would be a better symbol. Yeah.
Like a
Maybe an
hollow
S.
dot.
Oh.
Hollow dot.
Oh, yeah.
Oh, I think that one is reserved for something else. Yeah.
Or triangles.
Okay. Well, I think from the context, it's when you have a dot between vectors, it's the dot. Okay, so that's that. The next law was the one we have been spending time on over the past few days was Faraday, yeah. So that was E dot ds is equal to minus d dt of the magnetic flux, right? For this one. This is Faraday. And we have done enough problems of this one. So these three laws are in their final form and they're complete. These are just three laws. What's the fourth one? Ampere's. Okay. Ampere's law says B dot ds is equal to mu naught times
I enclosed.
times the current that gets through the surface or enclosed. Yeah. Now this one, we're going to add something to it today. But we're going to apply it first as is to calculate magnetic fields due to currents. This as a quick review, just like I did here. And then I will show you how to add that color. And we still have time for this. Let's apply Ampere's law. We're going to apply it to a problem that we have done, and then so we'll review that problem and then apply it to a problem that's slightly harder. And then the reason I'm doing that is because it will set the stage for what I'm doing. So consider a thick wire with current coming up. So here is the wire. The wire would have radius r. I'll draw it 2 or 3 times, but for the first one, I'm going to draw the current. This is current, right? That's coming out. So the current is coming towards you. Okay? It's a long wire. The radius of the wire is capital R, which which you can't see anymore. That's why I'm going to withdraw. So here is capital R. Right? And still, the current is still coming, but I'm just not drawing. And our goal is to find the magnetic field outside and inside this wire. So find the magnetic field outside and then inside. We'll start with outside, and then we go inside. We have done this in class a while ago, I remember, but I'm still going over it to demonstrate something. Okay. So we're going to find. By the way, the current is I. Right? That's the total current. Total current. So who can tell me what J is?
I over A.
Yeah, I over
I
A.
over A.
Okay, good. It's the current over the area, and the area is the total area, right? Which is pi r squared. It's a wire. So it's a circle. The cross section is a circle. So J, that is J, right? Okay, good. So let's find the magnetic field for R greater than capital R. Going to apply Ampere's law. So we need to choose, we're outside, so my little r is going to be outside. And here is my loop. My loop is going to go counterclockwise. The reason I'm going counterclockwise, because remember, if the current comes out and your loop is counterclockwise, the current that comes out is positive, right? So I would like to count it as positive, that's why I'm going to go counterclockwise. So my loop is going to go counterclockwise. Here is ds. This is ds. Here is another ds. They're all tangential. That's ds, right? So Ampere's law says v dot ds is equal to u naught times the current that gets through. Let's focus on the left side, and then I will worry about the right side. On the left side, I'm going to, I think we already argued many times that the magnetic field will be in the either counterclockwise or clockwise. Magnetic field is always circle. It's not diversion, it's not coming out. Because that would violate which law? If you assume magnetic field maybe just coming out. This one. Yeah, we violate this one. So, magnetic field, let's assume it's counterclockwise. If you get a minus sign, it means it's opposite to what you thought. So let's assume it's counterclockwise. ds is counterclockwise, so the dot product becomes just b times d. B times ds, right? Because they're parallel. So you get this, b times ds. And as long as you're a fixed distance away from the center, the magnitude of d is the same. So we move b to the outside. And then the sum of all the ds's is how much? 2 pi r. Good. Let's look now at the current that gets through. Okay. Here's our loop. Right, this is the thick wire, and our loop is here. This is our loop. The surface, I need to attach a surface to that loop. I'm just considering a flat surface. So the current just gets out through that surface, right? So, okay. So the current coming out is what? I. Just I, yeah. It's the total. Yeah. It's just u naught I, u naught I. And here it's u naught I. And so V would be u naught I over u naught I, which is not surprising. This is like an infinite wire. The wire is uniformly uniformly distributed current, so it's just going to be like a long wire, infinite wire when you're outside of it. Yeah.
Most wires act like uniformly.
Yeah. Right. Anything when it's not uniformly distributed is kind of mostly artificial for physics problems. So we're going to, and we're going to make it non-uniform. Now, how about inside? Inside the wire? Meaning R is less than capital R. Okay. So now the next one is going to be, here is capital R. And here is our new area. So again, but the current now comes out only through this area, right? The one here, this colored with red. This current only comes out from there. So same thing. B dot ds is equal to u naught times I for I enclosed. In this case, it's not the whole current, right? It's part of it. So B dot ds, it's going to be this, B times 2 pi r. That's B times 2 pi r. This is u naught. So here, I would have the integral of j times dA. Because j is the current over area, so j dA would be integrated, I would get the current. I'm making it into an integral, although it's unnecessary. It would be much simpler in a second. For the next problem, we have to do this. That's why I'm going to set it state for that. So we got B times 2 pi r is equal to u naught. In this case, j is constant or uniform, so we just put j dA. So B times 2 pi r is equal to u naught times j. J was I over pi capital R squared. And then, what's the integral of dA? Would be A, right? What is A? Pi R squared. Which R?
R small.
Little r. Yeah. Pi little r squared. Because we're talking about the red area. Okay? We got this pi cancels with this pi. This R cancels with one of these R's. We get B is equal to u naught times I over 2 pi R squared. And then 1 R is left, so good R. So that's the magnetic field.
Professor?
Yeah.
Can you break down what's behind dA? Like, what is dA?
What is dA?
Yeah, can you expand? Like, what's behind dA?
The integral of dA is A. That's all I care about for now.
Oh.
In this case, yeah. In the next problem, you want to know what dA is?
Yeah.
It's 2 pi r dr. I'm going to show you in the
2
next
pi r
one.
dr. With bound from 0 to r, right? Small r.
Integral from 0 to small r.
2 pi r.
I promise I'll come back.
Alright.
This next problem. So let's go to the next one, right? Next problem, I'm going to start it right here. So this is the second problem on Ampere's law, okay? Problem 2. So here is the current now, or the current density, I should say. Here's J. For this problem, you're given a current density that looks like this. It is some J naught times little r, let's say little r squared, okay, over capital R squared. Whatever. That's J. Here is the wire again. The wire has radius R. Radius R. The current is still coming out, but it's not uniform. Okay? It's not uniform. The farther away, the closer you are to the circumference, the larger the current density. So more current comes out from here than closer to the center. question is find the magnetic field inside and outside. Find the magnetic field inside and outside. The current is still coming out, so I would still go counterclockwise so that I can count the current clockwise. I don't want any minus sign. And then we will assume our magnetic field is also counterclockwise, and then see what happens. And so, for little r greater than capital R, B dot ds is equal to mu naught times the current enclosed. Here is my R, okay, R. And here I have the current enclosed. Let's see. We need to actually calculate it. So B dot ds, we're going counterclockwise. I'm assuming the magnetic field is counterclockwise. So B dot ds is just going to be B times 2 pi r. B times 2 pi r. How much current do we have here?
0.
None. Good. Perfect. There is current only here.
Yeah.
So here I have mu naught times the current enclosed, that's J times dA. J times dA. So J is this. This is J. What's dA? So I need to find the total current that gets out of here. And so let me remove this capital R from it comes somewhere there. So let me draw a maybe a different color here. I'm just green. That's okay. There it is. Let me take a little area here. The area here will have radius, let's say R, and the thickness here is, oh yeah, I'm using R twice. R prime? Alright, so let's use R prime. Okay, R prime. So this is R prime, and the thickness here, or the width, is dr prime. Okay? Dr prime. So what's the area? You have done this or what? Anytime. What's the area of that? So 2 pi r prime dr prime. That's dA. Okay. So yes, this area here, dA, is 2 pi r prime dr prime. That's the area of that little ray. Okay. So now we're going to continue. So I have B. Times 2 pi little r mu naught integral. J is J naught r over r squared r prime. Right? I have to put r prime for J because I'm integrating with respect to r prime. And then the area is 2 pi r prime dr prime. Okay. What are the limits of integration?
0 to capital R.
Okay, 0 to yeah. I want the current through the whole area. So from 0 to capital R. Yes.
So, Professor,
Yes.
I don't get it why you change the R, small r to R prime.
So that because I have an R here, and the meaning of this R is not the meaning of this R. If you can keep in mind that they're different, you can call it little r.
Okay, okay. Yeah.
The prime is going to go away anyways, because our limit is from 0 to r. There is.
Are we trying to find why is the limit from 0 to R?
So the current, there is current coming in from the middle, from everywhere in this wire, right? So I need to include the current that comes from 0 all the way to 0. Yeah. So that would be my, those are my limits of integration. know this. Yeah.
Can you explain again how you got J naught R prime squared over R squared? Is that only the J for the small?
J is given.
Yeah.
Yeah.
And then how did you know the one that you have in the integral with the R prime? What's that J? Like how did you get that?
How did I get this?
Yeah. And why is
So
R prime?
what does R represent in J?
Well,
The distance from the center.
Yeah.
The distance from the center here for the area, distance from the center to here, I'm calling it R prime for the area, so I need to call it the same thing for J. Because they're referring to the same distance. So that's that. Any other questions? So the rest is just a quick thing to go. First, I notice there is a 2 pi here and this 2 pi there. They go away. Let's see. So we have B. There is a little r left. Equals to U naught J naught R squared. Now, R prime squared times R prime is what? R prime cubed, right?
R
You
prime.
integrate, you get R prime to the 4th power over 4. You substitute from 0 to R, you just get R to the 4th over 4. Okay? R to the 4th. And then some of this cancel, so we get this. Magnetic field is U naught J naught R squared, right? This and this cancel, just left R squared, and then only number 4, and then little r, right? So again, once you exit the wire, the magnetic field decreases as 1 over r. Similar to this one. When you exit the wire, you have a 1 over r behavior. The farther away from the wire, the weaker the magnetic field. Okay? So that's the magnetic field outside, right? How about inside? Magnetic field inside the wire. So little r less than capital R. We're going to have the same integral. We're going to have the same integral. So we have this b dot dx equal to dot enclosed. Left side is going to be b times 2 pi little r, and then on the right side we have u naught integral j dA, and then we have j naught r prime squared over r squared times dA, which is 2 pi r prime r. What changes is the limits of integration. Yeah. So in this case, for this one, we want our we want the magnetic field here. So here's the wire again. This is capital R, and I want to know what the magnetic field inside the wire is. Distance little r from the center. So this is little r. I want to know the magnetic field here, so I need to only include the current here. The current that passes through that area. So the current passing through this area. Earlier, we needed the current that passes through the whole area. That's why the integral is from 0 to capital R. In this case, I only need the current that passes from 0 all the way to here. Only. Not the current here. This one is irrelevant. So the limits would be from 0 to where? In this next product?
0 to small r.
Little r. Yeah. So from 0 to little r. So again, this 2 pi cancel. So b times little r, u naught, j naught, r squared times. This becomes again r to the 4th over 4, right? But this time it's not capital R to the 4th, it's little r to the 4th over 4. And then we can cancel one of these r's. So we have b, which is u naught, j naught over 4r squared equals to little r.
Is there a magnetic field inside of the wire?
Yeah, that's the magnetic field inside of it.
How about electric field inside?
Electric.
Yeah, is there?
If it's an ideal wire, no, there is no electric field. Ideal meaning perfect conductor, no. If it's a little bit, if it has some conductivity, it will have some resistivity, and there will be some electric field. Yeah.
Oh.
Okay. So that's that. So I'll give you just a minute because I need to erase this side so that I keep writing here. I mean, I want to write here. Yeah.
So what is the difference of the problem one and two?
Problem one, the current was uniformly distributed throughout the area. It's yeah, it's a function of R.
Wait.
So please take a moment if you need the board, and then I'm going to erase. But go ahead.
Is current moving because they move from a higher potential to the lower one?
Yeah, so somebody is maybe driving a current. Yeah. There might be a battery attached somewhere. Yeah. That's might be the case. We don't really care how it's created. For us, for this problem, here is a current in a wire. Find the magnetic field. We're not worried about how the current was initiated. Zan?
Can you lower the other green board so I can take a picture of
This
it?
green board? Yeah, I'm not going to erase this one. Yeah. Can I erase this one though? Okay. So, all right. So you don't keep watching, you just erase. I'm going to pause. And then I will set it up.